Kepler's 3 laws. Kepler was a guy who lived a long time ago and had a gold nose. Okay? Cut his nose off. Well, he did. The Gnostics supposedly didn't do one. They made a gold nose for him. But he was a bit of a strange dude because he just looked at planets actually stars all the time. He came up with some laws according to some data. He's got 3 of them. The first one is every planet's orbit is an ellipse with the sun at a focus. What is that? What's an ellipse? That's like the oval thing. Yeah. That's right. So basically, sum it up really fast, he just said planets orbit in an oval, not a circle. Okay. Up until then, everything was going to be circles because everybody thought circles like a perfect shape. Everything had to be a circle. Come to find out, nope, doesn't work according to the data we have. So first thing he said was all the planets orbit in an ellipse. Second and third are the ones that are going to be, shall we say, your nightmares, because that's the one we're going to do the calculations with. And those are the ones that we count the most, or that we worry about the most. Because the first one's kind of like duh, isn't it?
Yeah.
Everybody kind of knows that, don't you? Not really, but that's okay. So, next one says a line joining the sun and a planet sweeps out equal areas in equal times. What does that mean? Someone tell me.
The line goes up, like an imaginary line.
Okay. Goes up where?
To the sun.
The sun.
And
from?
A line joining the sun and the planets.
Okay.
And the planet. And they're equal at equal areas in time.
So if we got the, whoops, let's get a pen. If we got the sun and we got a planet, what's the shape of the orbit?
Ellipse.
Ellipse. There we go. So now what?
It
connects those two. And what?
At equal area in time.
Okay, what's equal area?
I don't know.
So what's the planet doing? Orbiting. It's going around, right? It's moving. So if we start here and we let the planet travel one day, it's going to go where? Is it going to go all the way around in one day?
Oh, no.
That's how far? How long does it take to go all the way around?
365 days.
365 and? Come on, leap year. 365 and a? Quarter. Is what it really is. But actually, that's not even right either. It's actually a little bit different. So in one day, it moves to like right here, right? Does that make sense?
Sure. Yeah.
It just moves a little bit, doesn't it? If we draw another line, and then we fill this in, that's an area, right?
Yes.
Make sense? Is that okay? Everybody not sure about what's going on? Okay. So then, we're going to catch this thing, let's go like 5-6 months in the future. Boom, planet's right there, right? Got our line again? What's going to happen now? What's that law say? It says something about this area and the area we're going to get over here for that to go for 1 day. It's going to be the same, isn't it? So what does that mean? Where am I? Am I right here? Am I the same distance right here as here? No, what's it got to be? It's got to be further because the line's shorter, right? So I got to have more area here, or what looks like more area, because this area is just long and skinny, isn't it? And this area is like short and fat, right? So that means this one's I got to cover more here than I do here, don't I? So that's what this law really means, okay? We say that it sweeps out equal areas, but what it really means is when I'm close to the thing, close to what I'm orbiting, the planet's close to the sun, how fast is it going? Faster. than if I'm way out here, right? So the closer we get to something in an orbit, the faster it has to go. That's what it really means. That's what it's telling us. Yes?
If it slowed down, wouldn't it just crash
If it slowed down here or slowed down here?
Slowed down when it's close.
When it's close to the sun? Well, can it slow down?
No.
Because what's going to happen is it starts coming this way, and it gets closer to the sun. What happens to the force of gravity?
Yeah, it's stronger.
It gets stronger, so it pulls faster and faster, right? Does that make sense? And so that's what it does. It comes in and does a little shoo, right? Kind of a slingshot. If it's slingshot, then it'd be zooming out into space, not staying in orbit anymore, right? Well, but we do that, don't we? There's, long time ago, actually probably before you guys were born, where's my wheelchair? I'm getting old. We had a probe that wanted to go to this planet. What is that planet? Saturn. There you go. See, somebody can pay attention to my drawings, know what it is. And here's the sun. And what happens is, when we launch a probe out into space, we just make it orbit stuff. We make it go in circles. It doesn't ever just go like straight there. Okay? So we'd launch it and it would come like out the center. Okay? The problem was, on the day we were supposed to launch it, the weather was terrible. We couldn't launch it. So here we've got this millions and millions of dollars of space probe that we can't launch. And we missed the window, the time period, that we could launch it and get it out to Saturn. So NASA was scrambling. So what they did is they came up with another idea. And they actually had Venus in here. And what they did is they launched it, and it went by like Venus and the sun out to Saturn. Okay? But it was a way they could get it there. So they got these slingshots, they used gravity to speed it up and whip it out to Saturn. It was really quite clever to be able to do that. Because they hadn't thought about that at all until we missed this time period that we could launch it from Earth, send it out to the outer solar system to Saturn. So we had to go to the inner solar system. We had to make these big circles, these big orbits in and around Sun and the Venus. And we had to now remember, because that's the other part, I draw it like this, but what are these two actually doing? What's happening to Venus as this probe is traveling? Isn't it moving? So you've got to predict where it's going to be, when you need it to be there, so that that space probe comes by at the right angle or the right speed to get an assist and get thrown out. Okay? Yeah?
That's a ridiculous amount of calculating.
No, not really. No, not really. When you have a computer, it helps a lot, doesn't it? That's the idea. When we have computer models, we can predict it right now. How many good? Has anybody downloaded an astronomy app? So you can hold it up and see where stuff is? Okay. How does it know where stuff is? It calculates. We know where everything's going to move, how it's all going to move. We know all the little changes that it makes. And so you just hold it up on the day you're at, and it'll calculate where everything's going to be. Some of your apps, you can advance it. You can program in a date, and it'll move everything around. Boop, here's where it's going to be. A date and a time, so when you're standing out there at night, you know exactly what's going to be up. And it's all done just on those calculations. So your phone can do these calculations. Now this was done, let's see, this would have been early 90s, if I remember, was the scene. That was the name of the probe. So, a little more than your phone, but I mean, what NASA was working with to go to the moon was about a what? About a calculator. But it took up a room. Anybody seen the movie Hidden Figures? Why do you think things are called computers? Did you get that from the movie?
The people that did all the calculations
Were called computers because they did what? They computed stuff. They did the math. They had a room full of people that just cranked out the math. They showed the computer, didn't they, in that movie? If you've seen it, they showed that first computer. It was like a whole room full of stuff. Okay? And now you've got way more. You can do way more with your phone than they can with that. So it's really not a ridiculous amount. It's a pretty clever idea, though, to think that, hey, okay, where are these planets? Can we run it through? Can we do that? And nowadays, it would take nothing to program that in. But a pretty cool idea. So that's Kepler's second law. It really means faster when closer. Okay? So when you're closer to what you're orbiting, you're going faster than when you are further away. Or if we have an orbit, like if we have a satellite in orbit, the closer we get to Earth, that means we have to go faster. If we have a small orbit, we go faster than we have an orbit way out there. Okay? The third one says the square of the planet's orbital period is proportional to the cube of the semi-major axis. Got that one? Yeah, no, not really. Well, do you know what a square is? Okay, so we're saying that a square of something is proportional to the what? Cube of something. So the square of the what? The period. What's the period? There you go. So what's the Earth's orbital period of the Sun? There you go. 365 days. And that squared is going to be proportional to the cube of the semi-major axis of its orbit. How do you make an ellipse? What is that? It's just an oval. Now it's a special oval. It's not any. What's an ellipse? How do we define an ellipse? Like a slight. I'm sure that's the mathematical definition. I'm pretty positive. Slightly bent circle. No, not quite. There's a rule that it has to follow. What's the rule? Come on, you have to have had some geometry. What's the rule? What does an ellipse have? There's two things an ellipse has. Two what? No. Two curves. How do you get two curves? It looks like a big curve here. What are these things? What are those things?
Points.
2 points in the ellipse. Anybody in here in calculus? Anybody in pre-calc? Oh, SM3. Oh, you people are toast. SM2. Nobody's in 2? Anybody in 1? You actually learned this in 1. Okay, so, pre-calc. How do we define an ellipse? What are those two parts of an ellipse? When they come together, how'd you know that? Oh, you're busted now, you gotta know. That's right, when those 2 points are 1 point in the middle, it makes a circle. It doesn't make a straight circle, it makes a circle, it makes a perfect circle. No, an ellipse is not a stretched circle. Well, those are a focus point. Those are called foci. So if you take a string and tie one to here, one end to right there, and tie another end to there, and then put a pencil in it, you draw an ellipse. That makes sense? You got a pencil right here, and as I go around this, it will draw an ellipse. Because this line always stays the same distance. Okay. So from here to the ellipse, or to the outside of the ellipse, the perimeter, back to this foci will always be the same distance, any point on this ellipse. Okay. Grab your Chromebooks. Get them out. We're going to need it for this one. So it says here that the square of the orbit of the orbital period is represented by a capital T for the time it takes to go around. Yes? Okay? So it's the square of the period is equal to the cube of the semi-major axis. So what do you think I'm going to have you find? There you go. What is the semi-major axis of an ellipse? Find it. Let's define it and see what it is. You got it? Go ahead, Eric.
Major axis of an ellipse is its longest diameter.
Is its longest diameter. What would that be? So it's like this?
Oh, so it's half.
Is it half? So this is called the major axis or the semi-major axis?
The semi.
This
Oh,
is,
that's the major, and then half of it is the semi.
you should, I don't know. Is it?
I don't know.
Well, that's what we're finding. So in your definition, this is the major. Well, whoops, no I. Major axis, right? So what's the semi-major axis? Is it half?
It's not one of them.
Are you sure?
Yep.
You're reading it?
Yeah, the semi-major axis is one half of the major axis. And that's what
As
the
you read.
ray through the focus. And
So this distance is the semi-major axis. Does that make sense? It's not really that hard, is it? Major axis, that means the big one, right? And semi means half, even though a semi-truck's not half a truck. Right?
Yeah.
Yeah, somebody laughed. See, look at that. Even Howard's back there. He's got a smile underneath there. You can't see it, but he's got one. Okay? So, doesn't that make sense? Because this is like the orbit, right? If we were on the Earth going around the sun, that would be the radius of the orbit, isn't it? Does that make sense? Okay. So that's what we're looking at. That's what it's saying.
So that's from that like point, that's where you like tie the string to go around it.
Right here? Oh, wait. Tie the string. You mean right here?
Yeah.
On the circle?
Yeah.
Well, that's because both of these would come together, right?
Yeah.
So you just have one string that goes out and comes back, so it's always the same distance around, right?
Yeah.
Yep. And most of the other thing is, I way over exaggerated what most of the orbits are like. Okay? If we could zoom out to space, and there's the sun, and there's the earth, it would really look about like that. And that would be the ellipse. Okay? With how squashed it is called the eccentricity. And the eccentricity of most of the planet's orbits is not very great, which means it's not very squashed. To you and I, they probably look like circles if we would just get way out there. We probably couldn't tell too much. There's a couple of them that we could. Pluto you can, because it crosses actually inside of Neptune. Okay. So if you could stay out there for a few hundred years and watch it move, you can see that it's kind of moving. But most of the other planets are going to look really circular to us. So what we usually do is we just call it kind of an average radius. Remember last time we talked about AUs? And we said it like, well, I don't even actually here, I don't think I told you, 93 million miles is an AU. And that's the average, kind of the average orbit of the Earth. It's sometimes a little further, sometimes it's a little closer from the sun, or to the sun. But we kind of average it to be about 93 million. So it's pretty circular. It's nowhere near. The Earth would never look like anything like this going around the sun. Okay? It's pretty circular. But it still changes speed. We can record that. Okay? So that's what we're really saying here. Right here is, so we're just going to call that R because it's really kind of the radius of this orbit, right? Okay? It says that how long it takes to go around is proportional to how far away it is from the planet. Duh, right? How long it takes to go around is proportional to how far away it is, right? So if we were talking about this kind of a setup, and we had another planet here, and another planet here, which one would take longer to go around? The farthest one, right? Kind of duh, right? But when back in the day when we thought, or the prevalent scientific idea that was being proposed was that the Earth was the center of everything, this was pretty cutting edge, right? That's the idea. Now you've kind of grown up with it. Here's another example of something that's changed over the time. How many of you believe that there could be spacemen? Aliens.
Yeah.
Aliens. How many of you believe that there's a possibility that life exists outside of Earth? Okay? Now, you're all very accepting of that. Had you asked my high school, when I was in high school, one or two people would have raised their hands and we'd have thought they were kooks. They'd have been like the conspiracy theorists or thinking that people were living inside the Earth or something like that. What do I know? We've killed them all. We got rid of them all. We've already invaded all the other planets. You don't know about that. That's what Area 51 is.
Oh,
Amassing a giant space army from the Earth to go out and take over other planets.
Well, we would have found out if that.
What was that?
You remember that event?
Independence Day.
No,
Yeah.
no, no.
No, what?
Stormy area.
What if
Yeah,
that?
the storming.
Yeah, what about it?
That would have actually happened.
That wasn't actually Area 51.
Yeah.
Yeah, that's what everybody thinks that's Area 51, but that's not.
What is there?
I can't tell you. I'd have to tell you. You think I'm joking?
How do you know about area?
Because I work there? Well, what are you laughing at, man?
I didn't expect that. I was so sudden.
Oh, I'm serious. I know these things. You think Independence Day was just a movie? It's based on fact, man. There was a leak we had back in the 60s. They finally wrote a movie about it. Okay, so back to what we really need to talk about. Kepler's laws, right? So that's it. So the whole idea is that based on Kepler's laws, we can now make predictions to things like how fast do we need to go in an orbit? If we're going to put something in orbit, how fast do we need to make it go? Or, based on third law, we can also predict where things are going to be. You can't just put a planet anywhere you want to, or a satellite anywhere you want to. There are distinct places that you have to put them based on these two laws, making it go fast enough and having the period and the radius be proportional. Okay? So when we do satellites, we've got to calculate those things. And we actually, these are the basics of how we get to another planet. When we sent that probe, the Cassini probe out to Saturn, or any of the other probes we've done, we use this, the formulas we use are all based in Kepler's laws. Pretty sweet that this guy in, I think Kepler was like 1500, I can't remember. A long time ago, he came up with the stuff that's the basis for us to go to other planets, to go explore the solar system. It's kind of cool that he did do that. And he used data that they just basically used telescopes for and mapped out how the planets moved. And he came up with these laws based on all these mathematical models that he came up with. It was a pretty sweet deal. So, here's the part you're going to hate me for. Ha ha ha! This is the fun part though. This is where we get to calculate stuff. So, that's the second law, that's the third law. Today, we're going to look at some of these, just second law stuff. We'll practice with that. Okay? Now, you might want to, if you go to the unit, there's a link to the formula sheet that has these two formulas on it. You can print that out. You can use it on any test, quiz, assignment that we have. Okay? You do not have to memorize these things. Not at all. You don't have to memorize them. You just have to be able to use them and know what goes in those places. Make sense?
Yeah.
Okay. All right. Oh, wait. Can I move on, or you're still ready? You can go ahead. That's no problem. Just take the picture. That's it. Because now it'll be in the phone. You'll never look at it again. Even though it's on canvas, you just click.
Which one is it?
Just in case.
Are you in the unit?
Yeah.
So it should say something about a formula sheet. right? You're in unit 3. Oh no, you gotta be on the unit homepage, not in the module.
Oh,
So go to introduction.
okay.
No, go back here. Go back. You gotta go to the top of the module. All the way up, all the way up to the top of the module. There you go.
Oh,
That's the unit homepage that you get from the class homepage.
okay.
And then on there will be the link. Okay, so let's look at an example then. So there's our Earth. We want to put a satellite up, right? How far away do you want the satellite to be? How high? Somebody give me a distance. 20 kilometers? Okay. So we want it 20 kilometers from the surface of the Earth. That's a really low satellite.
With that
Yes.
study,
Did that even work?
Could it?
Well,
Well, anything's possible if we make it go fast enough. Now, there's all kinds of problems like,
that's the main
probably, yeah.
that's an issue, right?
That could be an issue because it could do what?
Burn up.
Okay, if it's going fast enough, right? What else? How tall is 20 kilometers? Run that thing in your Google. Put 20 kilometers equals miles.
That would be, let's see, about 13 miles.
Is it?
Close.
Right about.
Okay. There you go. So about 13 miles. Okay. Anything 13 miles up? How many feet is that?
That'd be 5,000 something.
5,280 times 13. 65,000.
So that's about the altitude of the U2.
Okay.
Just
So that's like top range of planes.
Yeah,
Is it going to run into anything?
possibly.
Is there any mountain that goes up that high?
No.
Tallest mountain in the world is
Mount Everest.
Everest. Goes up to an altitude of
21,000.
what?
21,030 feet.
I think it's a little higher than 21.
22?
I think it's 29. I think, but I wouldn't quote me.
It is.
Well, Is it
Well, I
29?
think it varies.
It's 29.
It gets bigger every year. So let's just say the tallest mountains top out at about 30,000. So we're not going to have to worry about hitting any of those. That's plenty high for that. But it's not very high. It's not high enough to get out of some of the top planes. If we've got special planes that'll reach up there. It's not like you're going to go hop on an airliner and go up to 65,000 feet. You'll be down between Mount Everest, 30, and usually about 45,000. How many of you have ever listened to when the plane announces how high you are? Oh, I pay attention to that stuff. I like to know where we're at, what's going on. So, 20 kilometers, it's not like it's outer space, but it's also not like we're going to run into a mountain. Okay? So, we want to know how fast does this thing have to go in order to stay in that orbit at 20 kilometers. Does that make sense? That's what we're calculating, is how fast does it have to go to be able just to go around the Earth 20 kilometers. So what was that formula? The square root of the G M divided by R, right? Okay? G, unique number. It's what? It's what? It's gravity. What do you mean it's gravity? Close. We call it, and you got to say it right, it's the gravitational constant. Because there's also, when you do some physics and stuff, there's also lowercase g. So those are two different things. So capital G is a gravitational constant, and it's 6.67 times 10
To the negative 11.
Oh, okay, yeah. Negative 11. Do you have units there? Did you look it up then?
Yeah.
What are the units?
Units, meaning,
The stuff that goes with it, like R, like distance is meters.
N
N is newtons.
newtons times M to
M
squared,
all over
kg squared.
squared. So we have newtons, that's N. What's M? Meters squared over kilograms squared. So this number, always the same thing. G's always the same thing. So if I were you and I had a calculator, I would type this number in and store it in the letter G in my calculator. So that way I can just bring up G and it's always going to be there. I don't have to keep typing it in every single time. Okay? So what's M right here going to be? What's M in the formula stand for? Nope, because this is a unit. That's the trick. This is a unit. This is a symbol in a formula. What's M stand for? The mass. Now you have to be careful because it's the mass of what we are orbiting. So in this case, it would be the mass of what? What? Earth, exactly. That would be the mass of Earth. It's what we're going around. So we can figure out how fast something needs to go to orbit you at any distance, right? If you have a mass, you apply gravitational force. It's probably not going to be very fast, though, right? Because it's not hard to escape your gravitational pull. So you don't have to go very fast to do that. Which would be interesting if you didn't. Because when you started talking to a friend, you'd have to run really fast away from each other to get away, right? If that was true. If we didn't need a big mass. And what is R? There you go, the radius. And when we say radius, what are we really meaning? The radius of what? Okay, that's where we got to be careful, because it is the radius of the orbit. So if this is my satellite, it is from here to here. That's the real tricky part, is it's not just this one, but it's also the radius of the Earth. Because we act like we do our calculations as if the Earth was just a point, and all the gravity came from that point.
Would that form a black hole?
Nope.
It is
Depends on how small the point is, right?
true.
But yes, we could have a black hole that is the same mass as the Earth. If you smashed it down small enough, yes, you could create it. There's something hopefully we will get to, and we'll talk about black holes. There's a thing called Schwarzschild radius. And that's the radius we got to smash it to make it a black hole. And we can figure out how big the Earth would be if it became a black hole. And it's going to be tiny. Not very much. So, we got G, we got the mass of the Earth, and we got the radius, right? And that's how we figured it out. So let's do it. So we say V equals the square root of G M over R. So we said G was 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. M, that's the mass of the Earth. What's the mass of the Earth? Oh, you want the 2 times 10 to the 9th. What? Oh, 10 to the 24th. Whoop, there we go. Kilograms. And the radius. Now the radius, remember we said was the radius of the orbit, or the height of the orbit, right? Plus the radius of the Earth. So don't forget, we got to add those two. So the radius of the orbit was, or the height of the orbit was, 20 kilometers. What's the, whoops, I want that. What's the radius of the Earth? That's the radius, not the diameter? Okay, so that's what you also gotta be careful of. Sometimes if you go look it up, it may give you a diameter, so make sure you've got the right thing. So that means the radius to the orbit really is what?
6.639.
There you go, kilometers. Okay, now here comes the next trick. What unit was that? That was meters, right? But what is this? Kilometers. So that means we have to make our radius what? Meters. How do you turn kilometers into meters? Move the decimal over how many times? Which one? 3 times, because kilo is 1,000, right? So 1 kilometer is 1,000 meters. So we move the decimal 1, 2, 3 places. So that's, 6, 3, 9, 1, and we just put 3 zeros on it. Meters. Okay? So that's where you got to be careful with our numbers, is that the radius here, we got a couple things we got to do to it. We got to add some stuff to it, and then we got to convert it into meters. Okay? So make sure you do that so we can get these right. So that says V equals the square root of 6.67 times 10 to the negative 11th newtons times meter squared over kilogram squared times, what was next? G times M, the mass, and that was 5.972 times 10 to the 24th kilograms, all over 6391000 meters. Good? Yes? Well, we haven't done anything. We just wrote the numbers
I
down,
know.
right?
But that's a lot of numbers.
That's a lot of numbers. No, that's 3 numbers. It's just a multiplication and a division, isn't it?
Yeah.
That's all it really is. You may look at that and say, oh, look, that's just terrible, but it's just a multiplication and a division, right?
Yeah.
So let's do the multiplication first.
Okay.
Do it one step at a time. Get your calculators. That's where you need your calculators. Remember to use the scientific notation button. You got to use the scientific notation button.
So do we have to put in the n times n squared?
No, you just put the numbers in. We'll talk about the units when we get done with the numbers. Okay, so we need 6.67 times 10 to the negative 11 times 5.972 times 10 to the 24th. What is that? Just do the top. That's all we're doing. We're just doing the top. Do it one step at a time so we can write it down and we can check our answers.
The E means.
That's right. It should be, remember, it should be a small capital E. Don't use one that looks like that. That's a number. That'll mess you up. Don't do that. Battery's dead?
Yeah.
Don't put it back in there. Hold on a second, though. Wait a second. Yep, they're dead. We're checking the brightness of the screen. Sometimes we need to.
What do we do about the N?
The units?
Yeah.
Hold, just wait on that. We'll talk about that when we get done with when we do the calculation.
So how do you add the Newton and?
Don't worry about that now. Just do the number. Tell me what the number is. Sorry. Say that again.
3.983 times 10 to
Okay, so now let's do 3.983 times 10 to the 14th divided by 6. Well, actually, let's do this. Let's check this first. Can everybody get 3.983 times 10 to the 14th? Yeah, that's right. Then we hit times and type your next number.
Okay.
Can everybody get it? Is that right? We got confirmation. Yeah? Everybody's okay with getting it? Yep, it says syntax there. Oh, I know what you're probably doing. My guess is we get the minus. That's right.
Oh, yes, it is.
So we need to go and use the negative.
Oh, gotcha.
Then we get it. There you go.
Thank you. Yeah, I got it.
We okay? Hiram, you got it? Just the top one. Just these two times each other to get that. Not yet? You don't need any parentheses. Because we're just doing those two multiples, so just type them in. And then we just do times. 0.97. 2. Yep. Everybody else? You? Okay. Okay, so now take this one. 3.983 times 10 to 20, 10 to the 14th divided by 6391, 000.
I got 6232.
Wait, 6, 2?
2, 3, 2. 2, 0.
Like that?
There's 2 2s. 3, 2, 2.
Like that?
Yeah. And there's zero, 1,
No decimal point?
0.33.
Okay. Do we need the decimal point? No, that's so tiny it's not going to matter.
I don't know.
What?
I don't know.
Well, confirm. Did we get that? You got something different? What else did we get? Give me some other numbers.
I got 62327
Like that?
It's 0.96, so would you round up?
I mean, sure, technically, if it's 0.96, we make that a 5, but how much difference is it going to make in that number? Not much. We're worried to about right there with little concern. We're very concerned to about right there, because that's about 1%. Yes?
I got 6.2322
To the what?
E7.
To the 7th, right?
Right.
1, 2, 3, 4, 5, 6, 7. That's that right there, isn't
Oh,
it?
they're the same.
So those are the same number.
Oh, gee, that's weird. It's the same
3, 6, 7, 8.
Except there's
So
one-
this one worries me.
There's one less.
It's close, but we're off by 1 power of 10, right? Did you use scientific notation button?
No, that's,
That will be it. That's going to add a second power of 10.
It's the, you just have to take away the 0. There's an extra
In this one? Yeah, but we want to know how she got it. And she probably got it because instead of using the E, we went times 10 to the power like this. So on your calculator, depending on how it reads it, it actually puts that 0 from the 10 in and raises it to the number of the power. So that's why you always want to use the E in the scientific notation button, because then the calculator reads it right all the time. Okay? So let's get rid of some of this so we can see what it is. I like that one best, because I don't have to write all the zeros out. So now what do we do?
I take
Square root it.
Okay.
So just hit square root and that number, and we get like that. How we doing? You got what?
I got that same thing except for 0.43.
So are we gonna worry about that? No, if it's off by decimal, we're not gonna worry. We're gonna quit worrying pretty much after that one. If you have 7, 8, 9, something, something, we don't care after that. We're good here. And actually, like on a test, I'd probably look right there. And if you got 7, 8, you'd probably say you're good. Does that make sense? Okay. Because a lot of this, because we've got big numbers, right? So depending on where you round and cut off, or if you use them all, if you're using your calculator, just recalling your answer, you're getting all the decimal places and everything, right? So we can end up having some things be different than that, okay? But now the question is, what are these units? Okay, so here's a trick. So that Newton, okay? Newton is actually how we measure forces when we're talking about physics and stuff. The physicists are lazy, so we don't want to write out a bunch of stuff. Inside of a Newton, what it really says is a kilogram meter per second squared. But we don't want to write all that out, so we rename it, we call it a Newton. Does that make sense? So instead of having to write that out every time, we just say, hey, whenever we see that, we're going to make it a Newton. So it does something interesting. So if we have newtons times kilogram, no, let's get those units right. Times meters squared over kilograms squared, times meters all over kilograms, right? Did I get those right? Did I switch them again? Yeah. So that's kilograms, the mass was up there, and meters right there. So really what's in here is, let's go here. Kilogram meter per second squared, that's that Newton, times meter squared all over kilograms squared, times kilograms all over meters. How about that for you?
That's the unit.
Well, that's all the units, right? Because we broke this one, we break that one into that stuff, right?
Okay.
But then we have the meter squared right there and right there, kilograms squared, kilograms squared, kilograms, meters.
Okay.
So we kept everything, but now we want to know what it works out to be. We got a lot of fractions in there, right? Everybody's freaking out, oh, fractions, we don't know what to do fractions. Actually, it's pretty easy, isn't it? Because this is on the bottom, doesn't it just flip? So what we can do is we get this to come up. We got some kilograms here, right? Kilogram, isn't that kilogram squared? So, oh wait, let's use the other one. So see you later, kilograms. Make sense?
Oh.
And this meter on the bottom and this meter on the top. See ya. So what are we left with? Meters squared, second squared. But what did we do at the very end of our calculation? These two?
Yeah.
Nope, they're divided. Because this is the same as being over a 1, isn't it?
Oh, okay.
So it goes on the top of this fraction and that one stays there. But what did we do, what process did we do at the very end of our calculation? We took the square root. So doesn't that take care of our squares? So it comes out in meters per second. So here's the trick. All it is meters per second.
All the time?
But as long as we put everything in our, whatever our units for G is, our mass is in kilograms, and our radius is in meters. This will work out to be meters per second. Okay? So that's the trick. But that's why it's so important that we got to have all those units on our G. We got to have the mass in kilograms, and the radius has to be in meters. Otherwise, it doesn't come out in meters per second. Okay? Make sense? Easy enough, isn't it? It's really not that hard. It looks freaky, but it's really not that hard. So we'll do some practice with it. Okay? Yes. Okay.
So.
Okay, no problem. Okay, looks like we're like out. Wait a minute. No, we're at 55, aren't we? I'm getting confused. 45 is all these days it confuses me. Okay? So that one, that's what we want to do. So that's how fast you have to go. Anybody know how fast that is? Fast, right? Yeah, you have no idea. You have no idea what a meter per second is, do you? So let's just do a quick thing, give you an idea here. So, let's see. I gotta think about this for a second. So take 7894. Just leave the decimal off. Take 7894, multiply it by 60. Multiply it by 60 again. And then divide it by 1,610. What did you get?
I got it.
What was it?
17,651.
What did you divide it by?
1,610. So you multiply it by 60 twice, and then divide it by 1,610. So we got that?
That's what I got.
There's how fast you have to go in a number that might be or might mean something more to you. 17,651 miles per hour. That's pretty fast, right? Yep.
That melted.
I don't know, I've never equated what kind of friction and heat we get out of that.
I
But
mean,
that's pretty fast, yes. We probably have a lot of friction. Mhm. I'm not sure, we'd have to look at it. But yeah, it would definitely be a concern, wouldn't it, going 17,000 miles an hour? But then again, how fast do the rocket ships that come back go?
around
Do we
about that
know?
speed.
Do they? I don't, you've never looked it up, have we? So we're not totally sure how fast they would go, right? But as we do some of these calculations and we get out there and find some of these other orbits, maybe we'll get an idea for what some of these speeds are. And we can see how fast some of these things are going. But remember, 20 kilometers, that's pretty low, isn't it? So according to Kepler's law, is that going faster or slower than something that's further out?
Lower. Wait, no, faster.
Faster. The closer it gets faster, right? So it's going really fast to stay in orbit. So if we go further out, then it goes slower. Yes? What'd you find?
So around about that speed.
Is what?
Re-entry speed for a rocket.
Okay. So that's about re-entry. So when we first re-enter, they get pretty hot, right? Okay. So, but this would be what it's going constantly to stay in that orbit, wouldn't it? Which is probably why we generally don't orbit where we still have atmosphere, right? We go to very thin or no atmosphere, or a small atmosphere if we can get, so it doesn't. Good? Good example for one?
Yeah.
We'll practice some more. Okay then.